the informal intuitive definition of a limit, or we say the definition of a limit of a function. Today's objectives is to gain understanding of the informal definition of a limit by looking at functions and their graphs. So the intuitive approach here is by graphing or by drawing, analyzing pictures to the greatest detail. We want to be able to understand and be able to write expressions with limit notation, limit from the right side of A and limit from the left side of A. The first example is a picture, and remember that NTS stands for not to scale, but we do want to indicate that 6 is a little bit further than 4. From this picture, let's look at x values approaching 6 from the left-hand side, and we want to look at the corresponding f of x values. So as x approaches 6 from the left-hand side, where do those corresponding f of x values go? And what if x values approach 6 from the right-hand side? Where do those corresponding f of x values go? Now keep in mind that 6 is not even in the domain of this function. 6 here is not even in the domain, but once again, if we look at this more carefully, as x approaches 6 from both sides, where do the corresponding f of x values go? Seems like the f of x values are approaching the number 4. Now notice 4 is not in the range of the function, yet we could say the limit as x approaches 6 from both sides, as x approaches 6 from both sides, we could say that the corresponding f of x values, or the corresponding outputs, are approaching the number 4, even though 4 is not in the range of the function. So that leads us to the informal definition of a limit. Informal definition of a limit. Suppose f is defined for all x near a except possibly at a. So in the previous example, a is actually 6. So the function is not defined at 6, yet we could still talk about a limit as x approaches a from both sides. If x values are sufficiently close to a, implies that the corresponding f of x values is arbitrarily close to L. L in the previous example is actually 4. So there's 4 there. Notice 4 is not in the range of the function. All right, let's say that one more time. Suppose f is defined nearly for all x near a except possibly at a, and if x values are sufficiently close to a, then the f of x values, or implies f of x values, is arbitrarily close to L. So there's your L. L is 4. Do the corresponding f of x value get arbitrarily close to 4? And the answer is yes. If we have that situation, then we'll actually write this new notation. The limit as x approaches a from both sides. The limit as x approaches a from both sides, we want to know where do the corresponding f of x values approach. If they approach L, then we could actually write this notation. Notice x arrow a there is a subscript. So when you're writing limit notation, keep in mind that the limit here, this is along a straight line, but the x approaches a there is a subscript. Remember, L here is defined to be a finite number. Finite, okay, meaning it's real and it's tangible. You can actually grab it. Okay, we'll learn about non-finite numbers very, very soon. Let's look at this example here. This is a function. It's a rational function, And notice we analyze domains right away, just like you do in algebra class. So let's look at the domain of f here. This domain of f, or the domain of this function, is negative infinity up to 5 union 5 to infinity. So it's all real numbers except for 5. Now what does this function really look like? This function looks like another function called g of x. And then what is g of x? Well, g of x is looking like 2x minus 3. But just got to remember, x cannot be what in our case? X cannot be 5. So why don't we go ahead and draw f of x. And this is y equals mx plus b. So we have a y-intercept of 0, negative 3. And we can go up to right 1 and draw another dot. We can go up to right 1 again and draw another dot, and so on and so forth. But there is something going on at 5. So once again, I'm going to use NTS, not to scale, but to rather get this sketch to happen more quickly, I'm just going to draw that and label this 5 here. So something happens at 5. There's actually a removable discontinuity. There's actually a hole there. There's something going on. What would have been that y value? Let's see. Let's count it. Well, what's g of 5? It would have been 7. If you're curious, it would have been 7. So that is actually our f of x. It looks like a line with a removable discontinuity. But however, what can we do? What can we analyze here? We could certainly look at the limit as x approaches 5 from both sides. Where do the corresponding function values go? The corresponding function values are actually getting closer and closer to what? They're actually going closer and closer to 7, even though 7 is not in the range of the function. So in general, does a have to be in the domain of the function? The answer is no. And does L have to be in the range of the function? The answer is no. All right. So even in the informal definition, we're analyzing very, very crucial specifics and situations. Here's a theorem. Suppose f is defined for all x near a except possibly at a. Then the limit as x approaches a from both sides. Where do the corresponding f of x values go? They go to L. If and only if the limit as x approaches a from the right side of f of x is equal to L, and the limit as x approaches a from the left side of f of x is equal to L. Now, if you're curious about the abbreviation for if and only if, we actually use IFF. And what is if and only if? If and only if allows you to read a statement in two different ways. So this is one way to read an if and only if statement. So whenever you see IFF, what you want to do is take the time to write the second way, or the second sentence. In this case, we have to read it backwards. If the limit as x approaches a from the right of f of x does get you the finite number L, and the limit as x approaches a from the left does get you the finite number L, big comma, then we could also conclude that the limit as f of x as x approaches a from both sides also equals the finite number L. So we're going to take advantage of this second statement, and this might give you a better idea of how to visualize limits using graphs. So what better exercise than to look at a graph? If you think you get the hang of this, go ahead and pause the video and try the exercises on your own, and then you could unpause the video to check your answers. The first one is an algebra question. We simply want to rewrite the expression f of 2. So f of 2 in this picture, that means the x value is 2. What is the corresponding y value? According to this picture, it is just the output is also 2. The next expression, practice writing limit notation. Okay, so practice writing this expression. The limit, let's say as x approaches 2 from both sides, where do the corresponding f of x values go? So let's look at this. Let's look at x approaches 2 from both sides. Where do the corresponding f of x values go? Now remember, where are the corresponding f of x values? They're right here. All right. The corresponding f of x values are going to 4. I'll do that one more time. As x values approach 2 from both sides, never hits 2, we want to know where do the corresponding f of x values go. The corresponding f of x values are going to 4. There it is. Okay, I'll circle that. Typically, you might see me write expressions going top to bottom. So for the next example, I'll do that. I'll write it going top to bottom. We'll have the limit as x approaches 4 from both sides. Where do the corresponding f of x values go? As x approaches 4 from both sides, where do the corresponding f of x values go? They're also going to 4. Oh, I said I would write top to bottom. So if I write it top to bottom, it'll look like this. And there's nothing wrong with that. Typically, in algebra, you are taught to write top to bottom. We will do both in this course. We'll go top to bottom, and then sometimes I'll go left to right. But when we have longer problems, you'll see me write top to bottom. That way you could see your substitutions a lot easier. Let's look at the limit as x approaches 5 from both sides. Where do the corresponding f of x values go? The corresponding f of x values are going to 2. Okay, the corresponding f of x values is going to 2, and that's what we do. We just write that 2 there. Hope that gives you some idea of how to interpret limits. You can certainly look at it as at one side at a time. As x approaches 5 from the left-hand side, where do the corresponding f of x values go? They're also going to 2. As x approaches 5 from the right-hand side, where do the corresponding f of x values go? They're also going to 2. So if you look at it one side at a time, you're hoping that each side goes to the same number L. And if that is the case, then we could write the limit notation. As x approaches a from both sides, we're hoping that it approaches a finite number called L.